yard still has a fair amount of snow on the ground because it has been incredibly cold, of course, this month. But look at this. It's sunny, sort of. Sunny, cloudy. Here is Fuji Baba. He is in meditative state, looking out the window. And here is Baji Baba. And here is a Suji Mama. And in fact, Baji was just now playing. Baji! He doesn't care about this toy anymore. He's done playing with it. But he was playing. In fact, it was very cute. And kind of wish I had filmed it then. Hi, Nausat. Nausat says, hi, how are you? Gurjar. Hi, Harsh. Happy USA. Nice show, snow. I will. Here it is. Here is Baji Baba. And here is the snow. Reese! Hello, I'm so sorry. Last night I had to be in the bathroom, but here I am. I promised no bathroom breaks this afternoon. And here is the snow. Now, Seth, are you good? Good on the snow? Reese is here. Harsh is here. Like done. Thank you. Can you like the live, everybody? Now, Seth, Harsh, and Reese. Very nice. Hello. Hello. I will share the live, but if you could share the live, that would be amazing too. We will talk about some other galaxies today. After we say hi to everybody and hang out for a little bit. Wow, awesome, says Nausat. Like maine kar diya. Thank you. Can we get 10 likes? Very nice snow. Thank you. How is everybody doing? How is it snowing where you are? How is everyone today on this Sunday afternoons? Baji's taking a nap. You know, I should have started this a little bit ago because he was playing with this toy just a minute ago. Stephanie says the cat is adorable. Thank you, Stephanie. How are you? Stephanie Murphy. Love it. Kanaga Sundar. Ah! Kanaga Sundar says, I love you. Same here. Love you too. Now Sat is saying cat is sleeping. He is. Look at this. He is sleeping. Sundar, how are you? Reese says, oh, Baji looks tired. He's not tired, honestly. Actually, maybe he is because last night he was fighting with his sister. He caused a lot of trouble last night. Last night he fought with his sister and made some huge noises. And I was like, is something bad happening in the house? But it was just Baji. He starts the fight and then he gets very scared of his sister. Sundar says, I'm doing great. Baji is so cute. Yeah, Baji is so cute. Baji. Let me show you Suji. Here is Suji Mama, who generally wins all of the fights that she does not start. And currently she's thinking that I'm going to give her a snack. But they have eaten, and there is my precious Baba. Where is my precious child? Hi, baby. Hi, Shona. All of them now think, since if I get up in my living room come kitchen, they think I'm going to give them a snack. I better sit down. Here is Baji again. Can you like the live, please? Can we get 10 likes? I know there's only 9 people here now, but could we please get 10 likes? Sometimes I manifest the likes, and one time I even got 50 likes. 50. So. Wow. What a day. What a day. I know you guys. I know some of you guys. What a day indeed. All right. So, if we have settled down, I'm thinking, hi. Hello. Hi says, hi, I love cats. Very nice. Thank you. Yeah, today is a kitty cat live. So sometimes I'm on the live myself, showing my face and hanging out with everybody, the kitty cats, and some physics and astronomy. And hi, Mad Hatter. What's going on? How are you? We are hanging out with the kitty cats, and I'm about to start on Galaxies. Now Sat says, Baji, I love you. Thank you, thank you, thank you. It's Baji, Baji, B for boy. This boy is Baji. So, I am just kind of chilling today. I think I will do a late live too tonight, but I wanted to do a day live while the sun is up and we can look at Baji, Fuji, and Suji in the nice lighting. And so sometimes I do a live like this where it's the kitty cats and then my voiceover talking about physics or astronomy or cosmology. And I did promise you guys I would talk more about the galaxies. We talked a lot about our own galaxy. In fact, we got some really good questions. I think Mad Hatter asked some really good questions, and we even made a new friend. I believe their name was Mega Ghost. So Mega Ghost, if you're here, then you should ask some more questions because that was really nice. And we kind of went through these questions and answered a lot of queries on our own solar system, planets, and things like that. So it was really, really nice. Hi, your cat is beautiful, says Lol. Thank you, Lol. Hi, Crazy Sick Wine. Hello. Now Sad says Baji. Crazy Sick Wine says lovely. And what is special today? What is special today is, look at this. There is sunlight. See how the sunlight is falling on the couch? So I'm going to sit over here for a bit. So the sunlight is hitting the couch. It's a good day to be alive. It is a good day to experience our very special star, the sun, which is a main sequence star, quite young. And it's only 4.6 billion years old. And it has only gone around in this galaxy, around the galactic center about 20 times. So our own sun, which of course we orbit, is also orbiting the galactic center of our own galaxy, the Milky Way. And it has completed only about 20 such revolutions. So our sun in the galactic sort of perspective is about 20 years old in that sense, if you will. But I don't want to confuse people too much. The overall age is 4.6 billion years old. But this sun is currently up. The sunset has been happening here in the Boston area later and later, thankfully. It used to be at like 3:30 p.m. it felt like, or 4 p.m. in December. Now it's more towards like 4:50 p.m. So I'm really happy about that. And this afternoon we will enjoy it as much as possible and hang out with the kitty cats. There's Suji Mama. She might cozy up with Baji. When they're not fighting, they're usually hugging and cuddling. So there we are. And may there be light, says Crazy Sick Wine. Absolutely. When will Venus pass through our sun again? I know it happened in 2012 from a theoretical perspective. I don't have that response off the top of my head. Venus will pass through. When will it? But I do know that Venus, Earth, Mars, Mercury, the rocky metallic planets, as well as the Jovian planets are things that we have kind of covered on the channel, more so as far as their compositions and what kinds of worlds they are. They're each their own world, each their own type of environment. And in fact, some of these planets, the Jovian planets, have a lot of moons that are also kind of entities of their own with a lot going on. And we have a really nice moon, a giant moon that we have also talked about. So I'm kind of recapping some of the things that we have recently covered. If you're interested, you should go back into the live tab of the channel and go one by one into the videos and listen to it. We covered all of these. Watched an interesting video about an unusual pulsar recently discovered that emits gamma ray bursts every 6.5 hours, which was previously not thought to be possible for a pulsar. That is very interesting. Gamma rays. Wow. Yeah, that is. Hello, Aditya. Aditya says, love from India. Welcome to India. Yay. This is also a good time I found for Asia people to be here because it's the nighttime in Asia, in India. So good evening, India. Good evening, Pakistan. Good evening to Asia and whatnot. I realized that when I go live in the afternoon here, sometimes more people from India can join. I was confused yesterday. It said you were live, but for 5 minutes at a time. Oh, those are my clips. Those are my videos. Sorry about that. That might be causing confusion. I'm sorry. Can you please like, if you're joining, could you please like the live? Thank you. Tap on the screen, please. So those were my, thank you. Thank you for liking the live. Can we produce gamma rays? Just liked, my bad. Thank you. So, hi Ram Candy. So some of my videos, I have been premiering them and they're basically shorter videos. It's a premiere. It's not a live like this live is a live, but premieres can be watched together with the people. Like I could watch them with you guys and have the live chat capability, but it's basically a video, like a normal video, but that's getting premiered where you can have the live chat during the viewing of the video. So sorry if that was confusing. Sorry about that. But what I will do from now on is try to schedule the premieres so that you know when it'll be going, and then not to be confused with my regular lives. Yeah. Awesome. Thank you. Thank you so much. Can we produce gamma rays? That's a great question. Just liked, my bad. Ram Candy, welcome. How have you been, Ram Candy? And Aditya and everybody, welcome to India. Welcome to US. Welcome everybody. Welcome to the UK, of course. So are you asking about the Earth? So the Earth is a planet. Generally, something like gamma ray bursts would be a great source for gamma rays. Gamma ray bursts are basically transient events that come from very, big cataclysmic events in the sky. They're generally extragalactic events, and they come from a couple different ways. You could have long gamma ray bursts, or you could have short gamma ray bursts. Will we see your lovely face today? I think tonight. I haven't, not right now. I don't feel like it. So gamma ray bursts is also a topic that I've covered in more detail in one of my other lives. But basically, there are a couple different ways you could have them. Long gamma ray bursts are associated with hypernovae. These are supernovae, but even more bigger than the regular supernovae. Now, supernovae is, of course, how a star dies. We have also covered supernovae in some detail. There's a couple different types of supernovae. So supernova in general, supernova is the singular, supernovae is the plural. Supernova is, of course, the process of death of a star, when a star becomes, for example, too massive, and it can no longer support itself and its own gravitation and its own sort of, gravitational body with its own nuclear reactor type of forces, like nuclear physics. When the nuclear reactions in a star sort of run out, and its gravitation is too big to kind of, hold together anymore, it will collapse. In fact, we talked about a particular type of supernova, which is very actually the more common type. It's a core collapse supernova, for example. Its core kind of collapses on itself, and those cause big explosions. And in fact, if it's a very big, if this type of supernova is, say, bigger than the usual supernova, sometimes we call that a hypernova. And these can basically create an environment of natural particle accelerators. And a lot of material is getting accelerated. We actually call those Fermi shock accelerations. A lot of sort of shells within, as it kind of explodes, expands, etc. Things can collide and cause shock accelerations of particles. And due to some of these processes happening within such an event, it's not a normal event or a normal environment anymore, right? It's a very extreme environment. And these are natural particle accelerator type of environments, and those can produce gamma rays. So generally, those are the significant producers of gamma rays. And in fact, gamma ray bursts are some of the most luminous events in the sky. If when they are happening, they're more luminous than an entire galaxy. Okay, so that's why Fuji, that's okay. Yeah, thank you for the question. So, your presence light up the room. Thank you. Fuji's presence, yeah. Gamma ray bursts are so introspectively brilliant, scary, and beautiful. It's mind-blowing. Thank you. Immensely energetic. Exactly. So, even though gamma ray bursts are transient, so the typical length is a few seconds only. They can be longer, but they can even be shorter. So I didn't tell you about the short gamma ray bursts yet, but the long gamma ray bursts, as I spoke, is associated with hypernovae. The short gamma ray bursts are associated with mergers of neutron star and neutron star, or neutron star and black hole, or black hole and black hole. So as you might know, a lot of different compact objects or even stars can sometimes be in binaries. They're not single, like they're not isolated like our sun. Our sun is a young single bachelor, but a lot of a lot of star systems are actually binary systems. When we resolve into them further, like the Sirius system even, I think Sirius is considered the brightest star in the sky, but if you look closer, it is actually a binary. So oftentimes there will be like a star and another compact object near it. It could be two stars, a star and a compact object, a star and a white dwarf, a star and a neutron star, two neutron stars, a neutron star and a black hole, and a black hole and a black hole. So I'm just naming different binary systems or different couples. The couples don't have to be all the same. Lots of variety. Thank you. Hello, Batman. And what happens when these things within binaries, basically, these binary systems, to put it short, are constantly losing gravitational energy. So as they do their little dance of orbiting around each other, they actually emit a lot of gravitational waves. The fact is that these are the two massive bodies are putting a dent in space-time, and as they orbit each other, their distance together is actually getting closer and closer, and eventually they merge. So because they're losing gravitational energy by coming closer and closer and orbiting each other, eventually they will run into each other and they will merge. And when that happens, during such a merger of a neutron star, or a neutron star and black hole, or two black holes, that is again another cataclysmic event that can release a lot of energy. And you could get gamma ray bursts from such an event as well. So those are considered to be associated with short gamma ray bursts, and those are the two types of gamma ray bursts that we can get, short and long. And what is super awesome is that we had some evidence of hypernovae being associated with gamma ray bursts in the past, and we kind of knew that, okay, gamma ray bursts, hypernovae, they kind of go together. So that sort of confirmation was already there for some time, for over a decade, I believe. And at this point, it's probably like a couple decades. But the interesting, exciting thing is that within the last, let me count, within the last decade, at this point, I guess it's going to be close to a decade of the first results coming out of the LIGO observatory. This is the Laser Interferometry Gravitational Observatory results. We actually now have confirmation that short gamma ray bursts are indeed actually associated with neutron star merger. This was just a thought before. This was just a theory before. But as we've mentioned sometimes on the channel, that there are plenty of theories and plenty of hypotheses, and that's completely fine. Doesn't mean that these theories are wrong, but generally speaking, physics and astronomy are experimental sciences, and it's not really totally understood until it's experimentally proven. So even though we had a theory that short gamma ray bursts were associated with neutron star merger, we did not have any observational evidence of that until we directly measured gravitational waves from this neutron star merger with the LIGO experiment. So if you're interested, you can look that up anytime. Ooh, thank you for liking the liking the like. Thank you for liking the live. Can I get 10 likes, please? So, hi, Johnny Boy. Hi, Batman. Hi, Ruan. Hi, Ruan. Ruan is saying, hey, cute cats. Thank you. Batman is here. My cat says, what's up? So, basically, thank you. Thank you for being here. So, to answer, so I think somebody asked about gamma rays, and you you basically prompted me to say all of the above things I just said, because gamma ray bursts are actually some of my favorite topics. It's one of my favorite transients. There are, different transients in the sky. In a sense, a supernova is actually a transient. It's longer. If you see a supernova appear in the sky, which we're actually kind of due for one in this type of time. We keep hoping that Betelgeuse will supernova and we will see a new star in the sky in the form of its supernova or and the supernova, when it does happen, it will be very bright, but then it will get dimmer and dimmer and eventually it will get a lot dimmer, and this luminous event may last something like a few months. So transient means that it's an event in the sky. It's not a more permanent object. So a supernova is a transient event. It's a pretty long transient event. There's probably going to be a lot of observations if a supernova were to, go off. And nowadays, the nice thing is that we do multi-messenger astronomy. So it wouldn't just be light that we measure from such a transit event. We would measure light, that too, in different wavelengths. We would measure gamma rays, X-rays, maybe radio. And then we would also look for neutrinos coming from the event, which is a whole other type of particle. And we may also want to see if we can be sensitive to any gravitational waves coming from such an event. So those are the, and also I forgot to say cosmic rays. So when it comes to multi-messenger astronomy, there is photons, which is light in different wavelengths. So photons of different energies, plus neutrinos, that's another type of particle that we can get from such things, cosmic rays, as well as gravitational waves. So nowadays, it's really in a multi-pronged way that we measure things, and we would if there was a supernova. But so think of gamma ray bursts as sort of something like that, but even more extreme and even more sort of short, depending on with what multi-messenger you're looking at it. The gamma ray emission part of a gamma ray burst is what it is generally sort of measured with in terms of time. So for example, if a gamma ray burst emits gamma rays for only 2 seconds, then you would say that the gamma ray burst is like 2 seconds long. But chances are that it's actually going to be emitting something else for a longer period of time. So just keep that in mind. Like there are definitions, and then there's then there's also more details and varieties in any particular situation. Okay. Johnny boy, can I ask a question? Yes, of course. Ask a question. Um, let's see. What other questions do you have? So hopefully that answered your question, Sundar. And I can always say more. My cat says, "What's up? I identify as a binary. Did you show and talk about it has a lot of mass? Hey, cute cats, good kitty. Mm-mm-mm-mm. Johnny, what's your question? Anime made me, okay. Beetlejuice is in space too. Betelgeuse, Betelgeuse is the name of a star. It's a red giant, and it is due for a supernova. I have a question on astronomy. Okay, well, Johnny boy, what's your question? It better be an astronomy or physics or cosmology question. And Batman, if you could tone it down a bit, or I will time you out. I think my mod is probably sleepy and currently doesn't care too much about modding because the mods are more active at night. So just watch yourself. Just watch it. Sometimes I don't really care, but sometimes if I'm bored, I will like punish you. So, okay. Okay. Let me put this down and share the live. You can be right here. Hi, Fuji baby. Ole baba, shona to tumi. Ekta shona to. Choto chele to tumi. Tu. Thank you, universe. Evil eye remove. শোনা তো ফুজি একটা শোনা ফুজি একটা ভীষণ শোনা প্রচন্ড শোনা ছেলে হাই বেবি kind of want to go swimming too today. Oh my god. Oh, and I said I would talk about galaxies. I keep forgetting what I actually said I would do. So I'll talk about the other galaxies or some other galaxies today as well. So we covered about our own galaxy, which of course is very special to us and whatnot. And it's a spiral galaxy, and it has all those spiral arms. We talked about how the different arms have different things and different types of materials and different Kayla! Kayla, how are you? Kayla, my child, how are you? How are you, baby? You tell him, Kayla. Kayla says, "You creep, leave Baji and my other lovers alone." Seriously. Kayla, you are saving me. I know, right? People need to learn to be more respectful. I was talking about gamma ray bursts just now. Stop being a creep to others or leave this live. That's right, Batman. We are ma'am to you. And ma'am is spelled with 2 A's. Just so you know. Just so you know. You should not stand. You should sit down. Sit down and just listen. Okay, Kayla, tell me everything. How have you been? How have you been, Kayla? Thank you for liking the live, by the way, everybody. Please do like. Can we get 20 likes? I'm going to talk about galaxies next. I just covered a little bit on the gamma ray burst stuff. I have been great. How are you and how's Baji? Well, you tell me. Baji's right here. We're good. We missed you. I went live at this time so that you could join, Kayla. Missed you. I've been dealing with all kinds of a variety of people, but missed you. Kayla was here for my Madame Curie live, I think. Right, Kayla? You were so supportive. I think most people did not care about that topic. I think Madame Curie is so badass, you know? Madame Curie is amazing. So I thought that everybody would love her, but but everyone just left the room and you were still here, I think. I missed you too. Oh, I have been busy all day and tired, and now I'm glad to be here. How is school, baby? No more fights, right? I hope nobody's giving you trouble. Those 8th and 9th graders. Okay. So originally I thought I would talk about the other galaxies, and I think that is what I'll do actually. For at least some time. So what time is it? It's 1:51 p.m. There's drama. What happened? Okay, you tell me your story. I'm gonna start doing the galaxy topic, but I'm gonna read all your comments, every single one of them. Tell us. Tell me. Oh my god. I can't wait. I'm reliving my childhood through Kayla. All right. So, thank you for liking the live. Oh my god. I dropped something very nice. So, today we will talk about some other galaxies because we have mentioned, we have spoken quite a bit about our own galaxy, which is, of course, a spiral galaxy with a lot of arms and things like that. In fact, I kind of want to show you real quick a picture of our galaxy so that you remember what we kind of covered. I got mad at my best friend for calling my other friends freak and nerdy, so I literally shouted at her and she told my secret about me, saying Elia is wanting Blake, and Elia said I hated her when I didn't. If you think you're funny, fight me right now. Oh my god. Oh my god. So was there a fight? Batman, you should... Batman, watch it. I will ban you. Don't you dare. Mm-mm. Don't you dare. Don't you dare. Batman's trying to hate. Don't do it, Batman. I will protect my children. Here. This is the Milky Way galaxy's artistic impression with all the spiral arms and everything. So we talked about this galaxy, our galaxy, a lot, of course. Next day, she acted all nice and I didn't even want to chat with her. Then she wrote my name on paper and put love hearts. Blake is my best mate. Aww. Kayla is no child. Kayla is a child. She's my child, and you better watch it. This is NGC 891, by the way, Kayla and everybody else. That is a spiral galaxy as well that we are looking at here, edge on. So we can take an image of that, edge on. And then this is another spiral galaxy, M83, that we're looking at face on in this image. So we can take images of these other galaxies, of course, because we're not in them. Sometimes we can take a picture face on, sometimes we can take a picture edge on. But for our own galaxy, of course, we need an artistic impression because we can't take a picture of our own galaxy from the inside of it. So Kayla and everybody else, we covered more facts and things like that about all right, Batman, you're on a 30 minutes timeout. So there we go. Now, Kayla, you continue your story because I'm catching up with you, and I will continue the galaxy stuff, and then I will read all your comments. So these are the spiral type of galaxies that we have been covering, and it's especially relevant, of course, because we live in one, which is the Milky Way. Now we will continue on to some other galaxies, if that sounds good. But Kayla, did you like those pictures that I just showed about the galaxies? I thought those were really pretty. So, okay. So now we will talk about some more galaxies, because did you know that when you look up at the night sky, most of the things you're seeing are actually galaxies? There are a lot of galaxies, just like there are a lot of stars in our own galaxy. Well, turns out there are just also a lot of galaxies. So what are some of these other galaxies like is something that we will now talk about for at least a little bit. Okay. Who's gay named Tristan, and he's not nice, but he says to everyone we're cousins. Oh. So the Hubble Ultra Deep Field is the result of 800 exposures of a single field in the constellation Fornax, with the Hubble Space Telescope summing to a total exposure of over 11 days. So let me show you what we're talking about. This is going to be figure 22 in this book. So let me show that to you first before I talk a lot about it. Oh. Okay. I see. It's a tough situation between them. Okay. So, one second. Sorry about the page turning. I need to find this picture that I want to show. Wait, what? Where did... Okay, let me put this down for a second. Or maybe this is fine. Am I missing it? Color figure 22. Okay, you know what? Forget it. So, the universe, we will skip the part that I was trying to show you. We'll get to the next part. The universe is as full of galaxies as a pomegranate is of pips. However, as late as the year 1920, there was still considerable uncertainty among astronomers about whether large galaxies other than the Milky Way galaxy actually existed. So, remember, before we started doing more observations and Hubble did his work, it was actually quite unknown whether there were other galaxies or not. And, okay. And especially other galaxies like the Milky Way was kind of unknown. This uncertainty was encapsulated in a pair of talks known to posterity as the Great Debate, given by the astronomers Harlow Shapley and Heber Curtis. Shapley maintained that the Milky Way was by far the largest collection of stars in the universe. So this is a while ago when they thought that. Curtis maintained that the Milky Way was only one of numerous large stellar systems or island universes, as they were sometimes called. The great debate involved the nature of small, spiral shaped nebulous objects known at the time as spiral nebulae. Shapley identified them as either gas clouds within our galaxy, probably sites of star formation, or small satellite galaxies orbiting our own galaxy. Curtis, by contrast, identified them as distant, large island universes comparable in size and shape to the Milky Way galaxy. So they used to call these things island universes. Just to imagine all of these stars in our galaxy and then there being more such galaxies was a lot. I think people could not wrap their heads around the fact that, there are just so many, this galaxy seemed like a really big one. And to think that there are even more such galaxies and whatnot, and understanding and estimating however many stars there are in this galaxy itself can be a mind boggling number. So, all things considered, I think people were just kind of unsure whether there were more galaxies or not. Maybe there were. There was a question about the nature of these small spiral shaped nebulous objects. And as gas clouds and nebula or nebulae in the plural will sometimes condensate to make entire solar systems like ourselves. So maybe they were thinking that there are such things hanging out and whatnot, and that's about it. But our galaxy is the main one. But some people thought that these things may actually be other galaxies. So this question and this understanding that there are a lot of galaxies was not always known. Even as of 1920, we are kind of not knowing this yet. So just about 100 years ago, we did not really know about all the many, many galaxies indeed that there are in the universe. So that Curtis was essentially correct, and that the Milky Way is just one of many galaxies started to become clear when Edwin Hubble used the Mount Wilson 100-inch telescope to observe the Andromeda Nebula, the largest of the spiral nebulae. So, as you know, Andromeda is a nearby galaxy, and they might have sort of known about it, but they did not properly observe it until, Hubble is doing his types of observations. And remember, when we spoke about the 20th century science developments, we spoke about how important Hubble's observations were. It really kind of changed everybody's views on our universe and what we could expect. So this Mount Wilson 100-inch telescope to observe the Andromeda Nebula, which is the largest of the spiral nebulae, this is very Very, very important. Hubble detected Cepheid variable stars within the Andromeda Nebula and showed that it is actually the Andromeda Galaxy. So, what they were thinking is just a nebula because if you can't see it very well, then you might think it's just a gas cloud just hanging out, something over there. But then when you observe it more closely and you find more properties of it and discover more objects in it, really it is another galaxy that we had now seen. So in 1929, Hubble published the result of his calculations that the Andromeda Galaxy, he believed, is at a distance of around 275 kiloparsecs. So that's how far away it is from us. This is not the end of the story, however. In the year 1949, so as late as 1949, the 200-inch telescope at Mount Palomar was put into operation, and Walter Baade, one of the first astronomers to use the new telescope, calculated that if the Andromeda Galaxy were at a distance of 275 kiloparsecs, then he would be able to detect its RR Lyrae variable stars. However, when he actually observed the Andromeda Nebula with the 200-inch, he found no RR Lyrae stars at all. So, a type of thing that he was expecting, it was not there. Consequently, he concluded that Edwin Hubble had badly underestimated the distance to the Andromeda Galaxy. So, as you can imagine, these figuring out these distances and figuring out what things one can expect in a different galaxy, etc., are still very much evolving at this point. Even the neighboring galaxy is not very close, right? So there were some confusions, but he thought that maybe the absence of having these stars would mean that this galaxy was more far away than Hubble had estimated. So his conclusion was that it was badly underestimated the distance to the Andromeda Galaxy, which had to be at least twice as far as Hubble's distance estimate for its RR Lyrae stars to be undetected. So, in fact, the best current estimate of the distance to the Andromeda Galaxy is around 780 kiloparsecs. So the initial distance of 275 kiloparsecs, the best current estimate is quite a bit more than that. It is 780 kiloparsecs. Hi, Kayla. How are you? How's it going? Continue your stories. Hubble's fundamental mistake was that he was comparing two different types of variable stars. The Cepheids he observed in the Andromeda Galaxy were luminous blue population 1 stars. He was comparing them, however, to variable stars in our galaxy that were population 2 objects within the galactic bulge. These population 2 variable stars, called W Virginis stars after their prototype, are only 1/4 as luminous as a Cepheid star with the same pulsation period. Thus, by applying the W Virginis period luminosity relation to the intrinsically more luminous Cepheid stars, Hubble was underestimating the distance to the Andromeda Galaxy by a factor of 2. So, as you know, as we have briefly covered in the past, the distances to different stars and different objects is not trivial in astronomy. So, understanding the distances to stars, for example, we covered one method, it was stellar parallax method. But there could actually be mistakes made in this process that could change your calculation a lot. And in this case, it turns out that the stars that he was using for Andromeda Galaxy to understand something about the distances of Andromeda Galaxy were population 1 stars, and he was comparing them to our population 2 stars. And we kind of briefly spoke about population 1 and population 2 stars as well. There are differences in metal richness. So let me read about that real quick as well so that we are comprehensive here. So even in our own galaxy, we actually have a variety of different stars. It's not that all of the stars are the same or come from the same generation and things like that, okay? So, in fact, in our own galaxy, which is quite a big and substantial galaxy, and a spiral galaxy. We actually have, I've said this already in the Our Galaxy Type of Life, but I want to just summarize really quickly here. The Milky Way has three main components. It has a disk, it has a bulge, and it has a halo. And these three parts actually have quite a bit different types of things in it. So, for example, population 1 stars, these are metal rich stars. So it's a little bit backwards. The population 1 stars are more metal rich. They are a later generation of stars. Population 2 stars are more older and lower in metals. So, because in the beginning of the universe, remember, there were very few baryons. It was mainly just hydrogen and a little bit of helium. And so the first stars, the first generation of stars, when they were formed, they were very metal poor. They might have formed and they might have become stars, but they pretty much did not have a lot of metals, and they did not make maybe a lot of metals. But then, as stars die and enrich the interstellar medium with all of their remains, which are more metal rich, those things, when they go on to become gas clouds and nebulae and make more new stars, the next generation of stars are generally more metal rich. So, our halo, so in our galaxy, the halo of our galaxy actually contains relatively low and relatively old and stars that are relatively old and low in metals. So we call them metal poor stars or older stars. So these types of differences and variety of stars exist even in our own galaxy. So when you're thinking about a completely different galaxy, there's no knowing ahead of time exactly what types of stars there may be. There could be a variety. There could be population 1 or population 2. You never know. So you have to keep an open mind when you're doing these observations. So Andromeda, turns out, had these blue, luminous blue population 1 stars. And when we look at the definition of population 1 stars, they are, of course, the stars that are younger and more metal rich stars. So keep that in mind, of course. And, if you're comparing to some stars here in the Milky Way galaxy, you might want to also pick some population 1 stars when you do that versus the population 2. So our galactic bulge is the component of our galaxy that is in the direction of the galactic center, around Sagittarius, the central bulge of our galaxy. It's about 1 kiloparsecs in radius, and it kind of sticks out above and below the disk. And at the very center of the bulge, there is a tiny nucleus bright at radio wavelengths. So basically, the bulge is something that you would see in infrared wavelengths, and the center of it you would see in radio and whatnot. So again, not every part of the galaxy is bright in the same wavelength. That's another thing to keep in mind. So our bulge has population 2 objects more, or at least the population 2 objects in our bulge were the ones that we compared with in terms of these, in terms of the Andromeda. So that's why he was a little bit wrong. He was quite a bit wrong. Okay. So next, moving on, we will talk about galaxy classification, and we will take a look at that. So Edwin Hubble, in addition to determining the true nature of the Andromeda galaxy, also devised the classification scheme for galaxies that we use today. So even though in these initial observations there might have been some mistakes, there might have been some uncertainties, and it was just getting started, right? In the first 10, 20 years of understanding other galaxies, breaking into these other galaxies like Andromeda itself is a big deal. So it's not such a surprise or shock if some things were a little bit wrong or off. It's always good to start with something, and then you can always correct and revise upon your findings. And that's exactly what he did. So in addition to determining the true nature of the Andromeda galaxy, which, remember, they thought it was just a nebula, but turned out it was a galaxy, He also devised the classification scheme for galaxies that we use today. So even today, we are using this same classification scheme that Hubble came up with about 100 years ago. Classification is an important first step in understanding the purely empirical classification of stellar spectra, for instance, which led to the physical understanding that the OBA FGKM sequence of spectral type is a temperature sequence. Galaxies, unlike stars, are not customarily classified by their spectra. In practice, Hubble found it was most useful to classify galaxies by their shapes. So, the way we classify stars using spectral type is a whole other story. We can talk about that too. You know, we know our sun is, for example, a pretty young star that is on the main sequence, and we also know that stars actually spend a lot of time on the main sequence, and there's a whole thing about how we classify stars. But when it comes to galaxies, he actually found it most useful to classify galaxies by their shapes as follows. The Hubble classification for galaxies is a morphological classification, and morphological means the Greek word is morphos, which means shape. So, morphological classification of galaxies is what we do with galaxies, where the word comes from the root is morphos, which is shape. So, the Hubble scheme, they're getting their food. The Hubble scheme is as follows, okay? So, these are the three main classes of galaxies that we get from the Hubble scheme. And these are elliptical, spiral, and irregular galaxies. So we have talked a lot about the spiral galaxies. We live in one. So we live in the Milky Way galaxy, which is a spiral galaxy. And we took a look at some examples of these galaxies, but we also have elliptical and irregular galaxies. Our galaxy is a spiral galaxy as a useful mnemonic device. The different types of galaxies are laid out in what's called a tuning fork diagram in a picture here that I'll show you soon. But in the tuning fork diagram, elliptical galaxies are on the fork's handle. The two types of spiral galaxies provide the two tines of the fork, and irregular galaxies are dumped off to one side. So we will look at this really soon here, but Hubble erroneously thought that the sequence shown in this diagram was an evolutionary sequence. He thought that maybe galaxies moving from left to right is how they evolved. But now we know that elliptical galaxies do not evolve into spiral galaxies. And elliptical galaxies derive their name from the fact that they look like smooth, glowing elliptical blobs with no dark dust lanes, no spiral arms, and no bright patches of star formation. These are all features of spiral galaxies. The dust lane, the spiral arms, the bright patches of star formation, those are all features of spiral galaxies. We don't see that in elliptical galaxies, okay? So I'm going to show you the picture here really soon, but I'll keep going for a bit. I'll let you take a look at that while I talk. So this is Edwin Hubble's classification system of the ellipticals, the spirals, and the irregular galaxies. So those are the three types: ellipticals, spirals, and irregulars. So elliptical galaxies look more smooth. See, more smooth, glowing elliptical blobs. So elliptical blob right there, elliptical blob right there, elliptical blob right there, elliptical blob right there. Right here too, see, elliptical blob, elliptical blob, elliptical blob. Whereas spirals, we have looked at spirals, they have the dust lanes, they have the spiral arms, they have the bright patches of star formation. So those are the spirals. They're quite different from the elliptical shape, okay? So some more facts about the elliptical galaxies. If you approximate the shape of an elliptical galaxy as a perfect ellipse, The size and shape of the ellipse are given by the semi-major axis A and the semi-minor axis B, where B is less than A. That's just true for ellipses. The shape of the ellipse can be described by a single number, and it might be the axis ratio B over A, or the ellipticity 1 minus q, or the eccentricity 1 minus q squared to the 1/2. So because we because we know things about ellipses, it's like you can even get some more facts about them because of that. The Hubble classification scheme assigns to each elliptical galaxy. So because we know things about ellipses, and we can do some math to give a further, see how there's a further classification, E0, E3, E5, E7. That's because we can kind of get some more detail on the ellipticity, and then assign them a further classification. Okay, so that's what this means. And then one unavoidable drawback to Hubble's method of classifying, this is Hubble's method of classifying about 100 years ago that we're still using, is that it relies on the projected two-dimensional shape of ellipticals. So see how this is a two-dimensional picture, 2D, ellipse, right? So of course, intrinsically, these are three-dimensional. They're spatially three-dimensional. So we can't scoot around to the side of the galaxy for an alternate view, unfortunately. So we don't know whether an E0 galaxy is a sphere or an oblate spheroid seen face on, or a prolate spheroid. So this elliptical galaxy has been given the ellipticity of 0, which is a further classification, so that we understand that this NGC 4486 is an E0 elliptical galaxy. NGC 4365 is a E3 elliptical galaxy, and NGC 4564 is an elliptical E6 type. So it's another further little classification given to the elliptical galaxies. But unfortunately, it's really based on these images and 2D images of what we see in the sky. We can't really scoot over to the side of this galaxy and see whether the ellipse has a, see its other dimension, basically. Okay, so just kind of keep that in mind as we think about these classifications. And next we will look at spiral galaxies, but let me finish up a little bit more about what this is saying. So although when it comes to the elliptical galaxies, although the shape of a single elliptical galaxy can't be unambiguously determined from its two-dimensional image, statistical statements can be made about the intrinsic shapes of elliptical galaxies after we look at large data sets. So it's fine. We have some way of, organizing these elliptical galaxies, even if it's serving mostly just in two dimensions. So next, we have spiral galaxies and a further classification of spiral galaxies. Here's some pictures of such spiral galaxies. So it turns out, of course, we know more about some spiral galaxies already on the channel because we have talked about them in terms of the Milky Way and some of the other spiral galaxies that we compared it to. But spiral galaxies derive their name, of course, from their spiral arms, seen most easily when we view the galaxy face on. So if you can image a spiral galaxy face on, then you will see its spiral arms more clearly. And spiral galaxies were first noted by Lord Rosse, R-O-S-S-E, in 1845 when he viewed M51, which is called the Whirlpool Galaxy, with the 72-inch telescope, the Leviathan of Parsonstown. Every spiral galaxy has a central bulge, a rotating disk, and spiral arms within the disk containing gas, dust, and star-forming regions. So we talked about this when we talked about the Milky Way. Indeed, there will be a bulge. There will be the bulge is towards the center. There will be a rotating disk, and there will be some spiral arms. And there's gas, there's dust, and there are brighter star forming regions. There are three main subdivisions. So when it comes to further subdividing them and further categorizing them, this is how we do it. The main classes are as follows, okay? SA. So let me find an SA example before I show you. Here it is. This is an SA example. So SA is big bulge, tightly wound spiral arms, little gas and dust. SB is medium bulge, moderately wound spiral arms, middling amounts of gas and dust. So that's an SB. And SC, which is small bulge and loosely wound spiral arms, lots of gas and dust. So let's look further. Here's an SB. There's an even more classification we will get into, but let me let you look at these. SA, SB, SC. So just a further classification of the spiral galaxies. And many spiral galaxies, perhaps even the majority of them, have an elongated central bar of stars. So now we're going to get into barred spiral galaxies from SBA to SBC. That's the next classification, further classification. So think about SB and then a further classification. That's a medium bulge, moderately wound spiral arms. And middling amounts of gas and dust. I hit the light above me, sorry. 1 second. I'm trying to sit on the countertop actually, so that I can show you the images and not hit anything more. I really like that the sun is on the book. So I'm utilizing the lighting here. Okay, so many of the spiral galaxies, perhaps even the majority of them, have an elongated central bar of stars. And these barred spirals, like ordinary spirals, can be further subdivided into SBA, SBB, and SBC, where the B stands for barred. Okay? Examples of barred spiral galaxies are shown here. So here's some barred ones: SBA, SBB, SBC. So NGC 4314, SBA, NGC 4548, SBB, NGC 613, SBC. So examples actually include our own galaxy, which has a bar. And though its degree of barishness is hard to tell from our location inside the disk because we're part of it, but the Hubble classification of our galaxy, we think, is SBB. And the surface brightness of the disks of spiral galaxies falls off exponentially with distance from the galaxy's center. So I will let you take a look. Actually, the barredness, we will get into a little bit more detail here, but I'll let you look at the pictures. Basically, now the spiral galaxies classification has extended to a type SD. So this is still A, B, and C, spiral barred. We might even have an SBD, but basically that represents spirals with minuscule bulges and huge amounts of gas and dust. So there's a lot of gas and dust and the bulge is very small, then that might be an SD type. A final type of spiral galaxy is the Magellanic spiral, also known as the type SM. Magellanic spirals are systems similar to the Large Magellanic Cloud, which has a prominent bar, rudimentary spiral arms, and lots of active star formation. So, Large Magellanic Cloud is something quite famous, spoken about quite a bit. And we've mentioned it ourselves here. Since the Large Magellanic Cloud has many young stars, some of them massive, it is host to the occasional core collapse supernova, like the supernova 1987A. So we have mentioned the Large Magellanic Cloud in terms of that. So there exist galaxies intermediate between spiral and elliptical galaxies. These are called S0 galaxies. S0 galaxies have flat rotating disks like spiral galaxies. However, like elliptical galaxies, they have very little gas and dust and no spiral arms at all. So they're sort of hybrid between the ellipticals and spirals. We're talking about galaxy classification here. And S0 galaxies are sometimes also referred to as lenticular galaxies, since they have big central bulges which give them a shape like a convex lens. And here is an S0 galaxy example for you. So this is NGC 3115. Sort of, yeah, it does look like a little bit like a lens, right? So there we go. This is NGC 3115, an edge-on S0 galaxy at 10 megaparsecs away from us. And the Large Magellanic Cloud is below that picture right here. This is Large Magellanic Cloud at 55 kiloparsecs. Right here, Large Magellanic Cloud, and the Small Magellanic Cloud at 65 kiloparsecs at right. These things. So next, so that was the elliptical galaxies and the spiral galaxies. Next, we will talk about irregular galaxies. So broadly classified, the galaxies are elliptical. We talked about that. They come with an ellipticity number, and we have a further classification, E0 and such, E0, E1 and such. We also have spiral galaxies that we ourselves belong to in the Milky Way. And then lastly, we have irregular galaxies. We will talk about that next. So I think I will let you look at, we will even talk about a supermassive black hole at the next live, I think. We've talked about it before, but I think it's interesting enough to talk about again. But here is the S0 galaxy. This is a type of galaxy that is between spiral and elliptical. So take a look at that, and I think I will cover irregular galaxies next time. So thank you so much for being here. Very much appreciated. And I will leave you with that picture, and we will go over these again later on. And that's where I'll cover irregular galaxies. Okay? Thank you. Hi Nelsat, how are you doing? gosh. Okay, I'm gonna have some water and then I'll let you guys go. You can also rewind and see the full discussion, okay? Thank you so much. Really appreciate it. Thank you.